Hello and welcome to the fourth lesson in the GCSE space physics topic. This is the one where we're just going to finish off now, and we're going to deal with some of the big questions in physics. You can see all the different things you need to know in this topic. It's quite a small topic actually, and we've covered quite a bit of it. I'm just going to cover those bottom three things. So what we mean by redshift, and then how redshift provides the main evidence for the Big Bang, and then think about some of the things that we don't know about the universe. So let's just think for a moment about our place in the universe. The universe is unimaginably huge, and there are so many stars. Here's a way of thinking about it: 10 to the 24, 10 to the power of 24, one with 24 zeros after it. That's roughly how many stars there are in the universe. That's a big number. But to give you a sense of just how big that number is, if you counted them, one every second, 1, 2, 3, 4, it would take you that many years. 20,000 million years. So that's more than 1,000,000 times the age of the universe. That gives you some clue just how many stars there are. It's a big universe that we're trying to make sense of. And when you look up into the sky, when you look at stars, really you're looking back in time. This is the Hubble Space Telescope, and that is a photograph taken by the Hubble Space Telescope. It's called a deep sky image. It's an image of very faint galaxies very, very far away. So in the words of Star Wars, a galaxy long ago and far, far away. So those galaxies there, 13 billion light years away. In other words, the light from those galaxies has been traveling through space for 13 billion years until it reaches your eye. So the light that's coming to you is light that travelled away from events that happened in the very distant past. It's 13 billion years is not it's got a substantial proportion of the total age of the universe. So when you're looking up into space, really you're looking back in time. So astronomers have always been trying to find out more about the universe, and we've looked up into space and we can make measurements, and this really is a story of how we can find out a great deal of information by making more and more measurements, because clearly we can't travel to these very distant places. And the first key idea that I need you to understand is a thing called redshift. And redshift is an example itself of something that's referred to as the Doppler effect. That is, if a source of a wave is moving relative to the observer, it changes the wavelength. And one of the easiest ways to understand it is if we look at sound. Sound is a wave. So I'm just going to show you a short video clip of a car which is moving towards an observer who's not moving, and then away. And what I want you to notice is how the note of the car horn changes. From the driver's point of view, the note of the car horn doesn't change. It's a continuous tone. But from the point of view of an observer who is not moving, the car is moving relative to them, the note changes. You can hear as it travels towards the observer, it's a higher pitch, and as it travels away from the observer, it's got a lower pitch. See if you can hear that. So it's quite a characteristic sound that we hear, but if the source is moving towards the observer, that in a way compresses the wave and makes the wavelength shorter. So a shorter wavelength sound is a higher pitch. So when the sound source is moving towards the observer, that means that the sound sounds a higher pitch. And the reverse happens when the source is moving away. It kind of stretches out the wave, it makes a longer wavelength, and that makes it a lower pitch sound. So we can hear that with sound, but what we want to understand is how that can happen with light. Light is also a wave, and that means that if we are moving relative to a light source, it changes the wavelength. Let me show you another short video clip.
The Doppler Effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Okay, so that's redshift. So we look up at the stars, and the stars are emitting this radiation out into space. And that's because of the nuclear reactions that go on inside them. We've talked about this. And the temperature of the star determines the colour of the light that's given out. So when we look at the colour of a star, we can tell things about how hot it is, and if we know how hot it is, we can infer things about the nuclear reaction that's going on. So when astronomers look up at the sky and they make measurements about the stars, they can analyse the light that the stars produce. That light, if we split it up, we produce a spectrum. But this spectrum has got little gaps in it. And so by looking at what these gaps are, we know that there are certain elements that are present there. If you remember the Bunsen burner and your flame tests from chemistry, the colour of the flames tells you about the elements that are present. So what's happening is those black lines are caused by elements within the star's atmosphere absorbing some of the wavelengths that are being produced. So astronomers can know quite a bit about what a star is supposed to look like. It's what colour it's supposed to be, how bright it's supposed to be, and all of that. So by comparing those measurements with what we actually see, we can tell about how much red shift there is. and we can tell from that the speed they're moving. So stars have what we might say an intrinsic brightness. That is how bright they really are if you were in a spaceship orbiting reasonably close by, and that depends on how big they are and how hot they are. But the apparent brightness is what we see from millions of light years away looking at these stars, and that apparent brightness depends on how bright the star really is, its intrinsic brightness, and how far away it is. Obviously, if you look at a light source from a long way away, it looks faint, doesn't it? Whereas if you look at it from close by, it looks brighter. So if we know about the nature of the star, if we know how bright it's supposed to be, and then we look at how bright it appears to be to us, then we can work out a lot of information about the star. So the only problem is we need a way of knowing how far away the star is. So this was worked out before we had we understood the idea of redshift. This little clip always makes me smile. This is what I was just talking about.
Okay, one last time. These are small, but the ones out there are far away. Small, far away.
So when we see a star that's faint, is it because it's small or is it because it's far away? Well, so if we bring in to the story, it starts in the early part of the 20th century, a lady called Henrietta Leavitt. Now, Henrietta Leavitt, she was a very clever woman. She got an astronomy degree in 1892. However, lady astronomers were not allowed to operate the telescopes. That's how the world was then. So she got a job as a computer. Now, at that time, a computer, that word has a completely different meaning to what it has now. And a computer was someone who computed things. In other words, she would sit in a room and analyze pictures from telescopes. So these are glass plates, because photographs then were negatives on a glass plate. And these women would analyze images taken over a period of time and looking for differences, looking for stars that change in position or brightness. And she discovered something really odd. She discovered a kind of star whose brightness varied. It got brighter and dimmer in a very regular pattern over a period of a few days. So this very predictable pattern, these stars are called Cepheid variables, and they could tell from these Cepheid variables how far away they were. So they were, by making quite clever measurements, they were able to work out how far away these stars were, and but they could compare that with the red shift. So this is the evidence that was eventually put together with by Edwin Hubble to work out the fact that distant stars had a greater red shift. So I've used the word parallax there. That's another interesting thing. How do you know how far away a star is? So imagine a star which is a long way away from the Earth. The Earth, that's that green dot there, is orbiting the Sun. So at one point in the year, we could measure the angle of that star to the Earth. Where do you have to look to see that star in the sky at a certain point in time? As time goes on, and the Earth moves around the Sun, so 6 months later the Earth is on the other side of the Sun, the angle of the star has changed. And if we know what that angle is, if we measure that angle, we can use some maths to work out how far away the star is. Now these are pretty clever measurements because the angle changes are really quite small, but through careful, patient and accurate measurements, Henrietta Leavitt was able to work out how far away these stars were, and were able to connect the type of star with their distance. And this gives us an independent measurement of how far away stars are, which meant that I'll skip that. Which meant that Edwin Hubble was able to build on this. So he discovered that the light from the stars is all shifted to the red part of the spectrum. It's got a longer wavelength than it should do, and distant stars are more red shifted. So he published a paper in 1929 that combined all these measurements together. So here's a graph that of the work that he published. So you've got distance and we've got the amount of red shift. And what he said, his Hubble's law was that the further away a star is, the more red shifted it is. And if it's more red shifted, that means it's moving faster. So the more distant the object, the faster that object is moving. So the only way that you can explain that is that the universe itself is expanding. The whole universe is expanding, because if you wind back time, ultimately all of those objects were in one spot. So a way of thinking about this is if the universe is like a balloon that's inflating, you've got a whole certain number of objects that are on that balloon, and as the balloon inflates, the objects get further and further apart. And since that time, in the almost 100 years that have passed since that publication by Edwin Hubble, scientists have been making more and more measurements that really back up that theory, and scientists are very confident that that is the correct explanation for how the universe began. Having said that, there's a lot that we don't know about. So we don't know that what all the energy is in the universe. There must be more energy than we're detecting, but we can't detect it at the moment. So it's referred to by physicists as dark energy, because the universe is expanding at an accelerating rate, and that's to do with this dark energy. We don't understand that. That's a big mystery. It's a question to be answered. Dark matter is another mystery. That's a different thing. It's completely different to dark energy. Two separate ideas. There must be more mass in the universe than we can observe because of measurements to do with gravity. And we're very confident about our measurements to do with gravity. There must be more material there, but we can't detect it. We can't see it. We can't measure it. So dark matter, that word dark, it just means hidden. It just means we can't see it yet. It's kind of a placeholder for an idea which someone is going to come up with eventually to explain what this is all about, in the same way that Einstein cleared up a whole load of confusions that existed at the beginning of the 20th century. You see, science works on theories, and sometimes people say, oh, it's only a theory, but I don't like that word only, because a scientific theory is a very special thing. A theory is an idea that can be tested and makes predictions. So if you have a theory like, say, the Big Bang, that will make predictions about what the universe is like, and then other astronomers go out and make observations to see if those predictions are correct. And if those predictions are correct, then that backs up the theory, and more evidence accumulates that backs up the theory, and that makes us more confident that that is the correct model for the universe. In this case, this is the same argument for any scientific theory, actually. Sometimes what happens is new evidence comes along that doesn't quite fit, that shows that, hang on, this doesn't work in this situation, and that means the model has got to be changed in some way. And very occasionally new evidence comes along that shows the model is completely wrong. So for example, Isaac Newton had lots of ideas about motion, and he published those ideas in the 1600s, and those ideas stood for a long time. It wasn't until the 20th century that Einstein said, well, Newton's ideas, they work on Earth, but they don't work everywhere in the universe. In fact, Newton only had part of the picture, and we have to incorporate Newton's ideas into a bigger idea. So his theories of relativity, for example, explain a lot more accurately how the universe works, and those laws work anywhere in the universe, not just near to Earth. So the key concepts for this part of the topic are what redshift is. You need to understand what we mean by redshift, and what does it tell us? It tells us that stars are moving away, and in fact, the further away the stars are, the faster they're moving, the more redshifted the light is from those stars. And the explanation for that is that all the stars once upon a time were at a single location, and that point source, that is the Big Bang. But we don't know the whole story yet. There's a great deal of evidence that supports the theory, but there are things that we don't know as well. That doesn't make the theory wrong, it just means we haven't finished finding out everything that we need to know, and that's kind of the exciting part really for science. So we've covered redshift, Big Bang, and the things in the universe that we haven't fully understood yet. In previous lessons we looked at orbits and satellites. In the lesson before that we looked at the life cycle of stars, and in the first lesson we looked at the structure of the solar system. So it's quite a small topic, it's quite an interesting one. I hope you've enjoyed it. You'll find a question on class charts for you to go and answer on this lesson. Thanks for listening.